Okay, Assalamualaikum and a very good day everyone. Welcome to week 8 of engineering mathematics. So for the second part, I'll be in charge. I will replace Dr. Liu Yemin. We will start with the Laplace transform topic. This is one of the powerful topic that we cover to solve differential equation in engineering. So I will start with the introduction of Laplace transform. The Laplace transform or in simple word we call the LT, is a method that help you to solve differential equation. More easily. So as engineering student, you know that you have a lot of you play with a lot of differential equation. It appears everywhere, for example in electrical circuit, mechanical vibration, control system, fluid mechanics, and many more. If you don't know what is differential equation, it is equation that contain at least one of the derivatives that of unknown, either an ordinary different derivative or partial derivative. Suppose the rate of change of function y with respect of x is inversely proportional to y, we can express it as dy dx is equal to k over y. So the challenge is solving this equation, this differential equation. It takes some time and it is very tedious. Okay, so when solving ODE, ordinary differential equation, directly using the time domain, using classical calculus, we often need to differentiate multiple time, and then we need to use integrate function. We need to integrate repeatedly, and then we need to use technique like variation of parameter, and also need to handle messy algebra. And this is very hard, especially if you have differential equation that has non-constant coefficient, and then the forcing function is discontinuation of piecewise, and therefore we use Laplace transform to help us to solve this differential equation. So what does the Laplace transform do? So we know that Laplace transform it transform time domain function into something that changes with time, like current. This Laplace transform, it transforms a time domain function. A time domain function is something like the changes with time, like current. You know that the current moving with time, it change with time. Okay, and then also voltage or displacement into a new function that we call as S domain. So the function of Laplace transform is to convert or to transform a time domain into the frequency domain, or we call it as domain, alright, or frequency domain. Okay, so when we talk about something that change over time, you can see that it's like we have like this graph. Okay, so this is the function, and then the time is moving, it's changing over time, the signal is changing over time, and we can see this is a time domain graph. And I mean, what frequency domains is like this. Okay, you can see that this is a frequency, and then we can talk about how something change over time for the time domain, like for example electrical current in wire, voltage in circuit, and then the movement of spring. We are looking at the time domain. Okay, this shows us how the value from this graph, we see that how the value changes at every moment, but sometimes it is more useful to us what frequencies are involved in this signal. So we can refer to this graph now. Time domain usually used in real-time monitoring. For frequency domain, usually used in analysis and design. The Laplace transform converts a function from the time domain, where it might be complex or chaotic, and we replace it to the S domain or frequency domain, which is a generalized form of the frequency domain. Okay, you can see that the frequency domain breaks in you can imagine it like the time domain is like hearing a full orchestra playing a song, and the frequency domain break it down into how much violin, how much drum, how much flute, and so on. So each instrument is a frequency. So this is the frequency 1, frequency 2, frequency 3, and the frequency domain help you to analyze and control each part of the signal easily. Okay, because when we move S domain to a difficult part of calculus like differentiation and integration, it becomes simple algebraic operation. Instead of dealing with the derivative, we will work with simple multiplication, and instead of integral, we will divide. That's why engineers, we love Laplace transform. They make the math easier to manage. Okay, or maybe I can give you a simple analogy, like you can think of the time domain as the problem written in maybe foreign language Japanese. Okay, so this is time domain. Time domain means is an FT, and then we translate the question is in Japanese, so you need to translate first to English. Okay, translate first to English. So English is the S domain, and then convert the problem in English, which is S domain. Once you solve the problem in English, now you can solve because it is in English, right? And then you can translate the answer back to Japanese using something what we call inverse Laplace transform. So when you already solve the problem, you can convert it again to Japanese, which is the time domain, or we call it as FT. So Japanese to English, we use Laplace transform, and then English to Japanese, or this way we call it as inverse Laplace transform. Okay, now that you understand what is the function of Laplace transform, we will look at the formal definition of it. So the Laplace transform of a function ft, the Laplace transform definition. Okay, the Laplace transform of the function ft. So ft, this is a in time domain. That's why it is in time domain. Yeah, so it's defined for all t which is greater or equal than 0. It is given by, maybe you can just try to memorize this formula, formula. Laplace transform of ft, close the bracket, is equal to this capital Fs. Okay, these are equivalent. The Laplace transform of ft, time domain, is equal to the capital of Fs, and this is the definition of this is the integration from 0 to infinity of exponential or e to the power of negative st, and multiply by time domain ft dt. Okay, so here so ft, what is ft? So what is this ft? Ft is actually the original time domain function. So the problem is always come from the time domain, yeah. And equal to Fs. What is Fs? S is the complex variable. This is a complex variable. Okay, of S is equal to the sigma plus JW. I think you have learned before in the matriculation, I think. And then the Fs, the total Fs is Fs is the Laplace transform of ft. Okay, this is equivalent to the Laplace transform of the ft. Okay. Okay, so here you know that ft is the original function, and this original function, it depends, this original function, oh sorry again, okay, this original function, it depends on time. Okay, and then as is complex variable, just now in practice it behaves like frequency. S is a frequency, and then fs is the transform version of ft, of the original time domain function. Okay, so this is the function in the s domain. All right. You can see from the formula that the Laplace transform, you can see from the formula here that the Laplace transform takes ft multiplied by an exponential decay factor of this e negative s to the power of negative st, and integrate from time 0 to infinity. And why it is from 0? Because we only care about what happened after the time 0. So in engineering, we deal with the causal system, meaning that the start at t equal to 0, like anything that happened before that is ignored. That's why the lower limit of the integral is 0. That's why we integrate from 0 to infinity. Alright, so maybe like you turn on the machine, the time will start from 0. It will not start from negative number. So this leads us to important concept of causal function. So what is the causal function? Okay, causal function. Okay, a causal function is a function that is 0 before t. 0 before t equal to 0, and only become active or become active at or after it become active at or after t equal to 0. Okay, maybe you can I can show you this graph. So this is the we are transforming ft into a causal function. So maybe this is the signal of ft, and then the causal function that we will look at is this one will be 0, and then after 0 we don't need to think about this part, and then after 0 we know that this is causal function ft multiplied by ut. Okay, note that since the limit of the above integral begin at t equal to 0, the behavior of the function ft at t less than 0 is ignored. Okay, this is ignored. Okay, so it is like I mentioned just now, it's like a machine that is turned off at first and only start working when you flip the switch at the time 0. And this concept is important because Laplace transform only work for causal system. So when you use Laplace transform, you automatically assume that the function ft equal to 0 for t less than 0, and then the function of ft is defined only for t greater or equal than 0. So the image is this image show how we convert the general function ft into a causal function, which is necessary when using Laplace transform. And again, causal function is a function that is 0 before time t is equal to 0 and only starts having a value at or after t equal to 0. So in engineering, remember, we only care about what happened after system start, not what happened before. That's why we focus on the causal function in Laplace transform. So now let's do a very simple basic example to understand how Laplace transform work. So now the question asks you to find the Laplace transform of the constant function ft. Find the Laplace transform of the constant function of ft equal to 1. Okay, so our ft now is 1. We can use the definition of Laplace transform of 1 is equal to, now you remember what you need to do first is integration from 0 to the infinity, and then multiply with the e to the power of negative st, multiply by 1 which is the ft dt. Okay, this one, when we integrate this one is 1, no need to think. When we integrate this, it will become e negative st, because this is we differentiate it to dt, so we have negative s down here, so negative e negative st over s. Alright, so here we need to substitute 0 and infinity. So when we have here negative e to the power of, when we substitute to t, we have negative and s and infinity, we know that it is e to the power of infinity, and then minus e to the power of 0 is 1, e to the power of 0 is equal to 1, so it will become 1 over s. You will get e to the power of infinity is 0, so 0 plus 1 over s, we get 1 over s. So our fs, which is the Laplace transform of ft equal to 1, is equal to 1 over s. Find the Laplace transform of exponential function ft equal to e to the power of at. So Laplace transform of ft, L to the power, curly bracket, the Laplace transform of our ft is eat, right? So what you need to do first is you need to integrate from 0 to infinity, from 0 to infinity, and then we multiply by e negative st. Our ft is eat dt, and then what we got here is integration from 0 to infinity. We know that it can become like a can this one and this one, they are just plus each other, so we put it as a minus st dt. So when we integrate this, we will get e to the power of a minus s t divided by a minus s, a minus s, and then we integrate it from 0 to infinity. Okay, when we try to substitute e to the power of infinity, we will get as minus e to the power of 0 as. So here is 0 minus 1 over as. So our solution is 1 over s minus a. So this is the Laplace transform of the function exponential function e to the power of at. So here, let's summarize what we have learned so far. The Laplace transform that convert the time domain into the frequency domain. So time domain is ft and frequency domain is fs, and it simplified the process of solving differential equation. It only applied to causal function, meaning the function start at t equal to 0, and when we use exponential kernel e to the power of negative st, filter the function one transform, we can solve algebraic equation in f domain, where I show you later, and we can convert the solution back to the inverse Laplace transform. So in the next part, we will discuss one of the important properties of the Laplace transform, which is the linearity, and we will also learn about how to use the Laplace transform pair table, which is like a cheat sheet to solve a problem quickly. All right, now let's look at the topic of linearity. All right, 1 minute. Okay, what is linearity? Okay, for any function of ft and gt whose transform exists, and any constant ab, the transform of aft plus bgt is given by 1 minute, I will try to draw it here. Okay, topic of linearity. Linearity 8.3. The topic is 8.3. Okay, if you can refer to the notes, you can see, you can have this formula where the Laplace transform of A is a constant multiplied by ft, one of the function in time domain, plus, and b is also a constant, and gt is also a signal or a function in the time domain. Okay, so this one is equal to this line is equal to a, the constant. You can bring the constant out, and the Laplace transform of ft close the curly bracket plus b, Laplace transform of gt, okay, where you can see that, okay, the a and b, this a and b, there are constant mean like a number lah. And ft and gt, these are the function whose Laplace transform exists. So this is the function in time domain. Alright, in simple term, this means that if you have a sum of function, like function multiplied by a constant, okay, you can take the Laplace transform of each part separately. Laplace transform of ft, Laplace transform of gt, and just multiply by its constant. Okay, like analogy, you can imagine making a fruit juice blend, mango plus orange. So this function is mango, this function is orange, and the Laplace transform lets you to process each fruit separately, then just mix the juice. Okay, just mix the juice. You don't have to blend them first before processing it. It works the same way either. So now let's apply the linearity rule to one of the equation here. Now let's find the Laplace transform of ft equal to 3t plus 5. So from here you know which one is constant, which one is function. And from the Laplace table, where I will show with you later, or you can refer to the notes that you have. Inside the note that you have, the Laplace transform of t is equal to 1 over s squared, and then the Laplace transform of 1 is equal to 1 over s. So the Laplace transform of this function 3t plus 5 is actually equal to, you can put the constant outside, the Laplace transform of t, and then plus 5 outside the Laplace transform of 1. It will become like this 3. The Laplace, when you please refer to the Laplace transform table in the notes, you can find the Laplace transform of t is equal to 1 over s squared, and then plus the Laplace transform of 1 is just 1 over s. So here, very easy to solve now, right? So here you can get this is 3 over s squared plus 5 over s. Okay, done. See how easy it was. This is a powerful linear, this is the power of linearity. Okay, so whenever you see a function that is sum of scalar multiple, just break it into parts. You just use Laplace transform on each part, then combine the result together again. Okay. Alright, now you have we have seen how linearity works. Let's introduce a super helpful tool, which is the Laplace transform table. The Laplace transform table. So what is this? Okay, Laplace transform table. This table show you some common function and their corresponding Laplace transform. You will use this table throughout this chapter, and so it is important for you to become familiar with this. So what is Laplace transform pair? Laplace transform pairs. Okay, Laplace pair is simply a matching set. It's a matching set. Okay, so ft, we perform Laplace transform, it will become capital Fs. Okay, it become a function of Fs in the S domain after applying the Laplace transform. Okay, this is for the common Laplace transform table. Please refer to the note, and you can see that this is the common thing that you have in the table, which is this is ft, this is the Fs. You know what is the Fs? The capital of Fs is actually equal to the Laplace transform of the time domain function. Okay, what is this? It is equal to the integration of from 0 to infinity of a function ft multiplied by e to the power of negative st, and you differentiate it with respect to dt. So the common Laplace transform pairs, we have ft, and the Fs. So Laplace transform of 1 is equal to 1 over s, and then the Laplace transform of t is equal to 1 over s squared, and then the Laplace transform of just now e to the power of at is equal to 1 over s minus a, and then there's a lot more. You can just refer to the table later. Okay, you don't need to memorize all of them at once, but just be more familiar with this, so that the more familiar you are with this thing, the more faster that you can solve the problem. Okay, we can look at one exercise here. You please find the Laplace transform of 4. Okay, a Laplace transform of 4. So very easy, just from the table you can see here the Laplace transform of 1 is equal to 1 over s, where 4 can become the constant here. So the Laplace transform of 1 is equal to 1 over s. So the Laplace transform of 4 1 minute, Laplace transform of 4 is equal to 4 Laplace transform of 1 is equal to 4 multiplied by 1 over s, and you can get 4 over s. Okay, and maybe the second one, find the Laplace transform of 10t to the power of 6. From the table you can find that the Laplace transform of the this is a bit difficult. T to the power of n is equal to n the factor of n divided by s, n plus 1. So for n equal to 6, the Laplace transform of t to the power of 6 is equal to 720 divided by s7. Okay, so the Laplace transform of 10t to the power of 6 is equal to 10 720 multiplied by 720 and then multiplied by s7 is equal to 7200 s7. And from the table you can also find what is the Laplace transform of e to the power of 3t. From the table, L t n is equal to n to the factor of n as n plus 1 as n plus 1. Okay, so for the n equal to 6, the Laplace transform of t to the power of 6 is equal to the Laplace transform of e to the power of negative at, which is a, you can see that a is actually 3, is equal to 1 over s minus a equal to 3, and then the Laplace transform of e to the power of 3t equal to 1 over s minus our a is 3. Okay, so the final tips here, you can use Laplace transform like a dictionary. You can try match the time domain function with the Laplace equivalent and combine with linearity when handling expression like 5t plus 3, 5t plus 3, and then 2e to the power of 4t plus sine 2t and so on. So you need to practice a lot here, because practice is the key, and you will be using this table for a lot in the future topic. So in the next part of the lecture, we will look at inverse Laplace transform and how to bring your solution back from S domain to the time domain. We will also learn partial fraction, which are essential when working with backward with Laplace expression. Okay, before we move on to more advanced topic like partial fraction and inverse Laplace transform, maybe we can have a moment to practice how to actually use this Laplace transform pairs table. So this is the Laplace transform pairs table. Okay, so we usually use this Laplace transform pairs table to solve some basic problem. Okay, you don't need to memorize this, you can just refer it when you want to solve the question, and this is one of the important skills that you will need. And the good news is that it's easier than you think. When you understand the step, it is very easy. So what is Laplace transform pairs table? Okay, it is a lookup table that show you the relationship between the time domain function, which is this ft, this is time domain function, and the capital Fs, or the Laplace transform of ft, is in this column. You will often see it's written like this: the Laplace, the function, the time domain function ft interchange with fs, the Laplace transform of the ft. So this table is like your cheat sheet. It saves you from doing the long integration. So when we use this table, okay, when we were asked to find the Laplace transform of a time function, you can just match the function with the correct formula in this table. I will show with you the step later. And then the second one is when you are given a Laplace domain expression, or if you are given this, you can use this table to find this, or if you are given this, you can use this table to find this fs. Okay, that is called the inverse Laplace transform when you want to change this fs to the ft. Alright, so today we will focus on the first case using the table to solve Laplace transform problem. We show you step-by-step guide on how to use this Laplace transform table. So the step one, the first step is to identify the form given by the function. If it is a basic function like 1, if you can see here, 1 t to the power of 2, it is or it is something more complicated, basic or complicated. And then step 2, you need to find the corresponding entry in the Laplace transform table. You basically just match it exactly to the function in the table. You can use linearity rule to break it into smaller parts so that you can compare, or you can substitute into the formula. You can write down the Laplace transform of each using the term in the table, and step 4, we can combine all parts if needed. So if you have given multiple term, then you can add them together. Okay, I will show you example number 1 for this Laplace transform pairs table. So maybe you can find the Laplace transform of the Laplace transform of ft. 1 minute. The Laplace transform. Find the Laplace transform of ft equal to 2t plus 3. Okay, so step 1, you break it into two parts. So ft is equal to 2 dot t plus 3 dot 1. Okay, so from the Laplace transform table, we know that the Laplace transform, so 2 is just the coefficient, right? So 2, and then t, you can find t from the Laplace transform table. It is equal to 1, the Laplace transform of ft is equal to 1 over s squared. So you can replace this t with 1 over s squared, and then plus 3 multiplied by 1. So the Laplace transform of 1 is equal to 1 over s. So you will have 2s squared plus 3 over s. Okay, so here is, you can see it is very simple to solve this. You can solve it further by multiplying 2 plus 3s divided by s squared, and now I can